Welcome everyone and thanks for joining us today. My name is Matt Willard and I'm the Senior Marketing Manager at Fluence Analytics. Before we get started, I want to point out the chat feature at the bottom of your screens. If you scroll down to the bottom, you'll see the chat button, and there you can pose questions to our panelists, which they will answer at the end of the webinar, or you can chat with me live during the webinar. Fluence Analytics is a startup headquartered in New Orleans, Louisiana that spun out of Tulane University in 2013. We manufacture industrial and laboratory monitoring solutions that produce continuous data streams and enable real-time optimization. This leads to improved process control and faster R&D periods. Today's webinar will discuss the problem of protein aggregation, the importance of aggregation kinetics, developing more stable formulations in less time, and ARGEN, a lab instrument by Fluence Analytics. Our panelists today are Dr. Danny Chow and Mike Drinsky. Dr. Chow is the president of Compassion Biosolution, and he is a renowned industry expert with more than 15 years of experience in formulation development and protein analytical technologies. Mike Drinsky is the CTO of Fluence Analytics, and he has more than a decade of experience developing ARGEN's hardware, data analytics, and proprietary technology. Again, thanks for joining us today. This is our company's first webinar, and we are excited to have all of you. Now, I'll turn the webinar over to Mike.
Thank you, Matt, and thank you everyone for attending. It's a pleasure to give our first webinar here. First thing I'm going to start off with is going over an outline of the presentation. The first thing we're going to look at is what is the problem of protein aggregation. We'll go into a couple of topics here, conformational, colloidal, and interfacial stability. Then we'll look at an introduction to ARGEN and the solution to this aggregation problem. Once we understand the ARGEN technology and what it is, we'll go into some of the topics of using the ARGEN system to understand thermal stress, stirring stress, as well as other types of excipient and buffer concentrations for formulation development. And then finally, we'll wrap up with key benefits from the ARGEN technology and conclusions with open opportunity for questions from there. All right, so what is the aggregation problem? As we're all well aware, we're here for this presentation. We understand that aggregation is a problem in the protein and peptide kind of industry, where you're developing formulations and drug therapeutics. Things that come into play that cause aggregation, as typical of understanding, are temperature, stirring, exposure to liquid air, and material interfaces that causes aggregation. Understanding other cases which like thermal cycling, freeze-thaw, or lyophilization also cause aggregation. Now, what formulation scientists typically try to do is develop these formulations so that you keep the molecule protected from these aggregation behavior. And the different kind of factors that we can play with are the pH, buffer concentration, ionic strengths with different salts, excipients, and also surfactants. Now we're going to propose here the understanding of the two-fold or two-step model for the unfolding and diffusion limited aggregation. Now imagine the native protein is conformationally stable here. As some type of stressor comes into play, it might cause a partial unfolding of the molecule where you expose hydrophobic zones on the molecule, and then those hydrophobic zones can come together, stick together, and then cause higher level aggregates. Understanding this two-step model gives us the ability to understand also the limiting conditions of this aggregation behavior. Overall, Arrhenius behavior can give you us information about the colloidal and conformational stability of the molecules. Stochastic information, which we'll get to in later, is understanding really what are these kind of interactions that cause aggregation that are not limited to the temperature or stirring kind of stresses. And then there's also interaction behavior, understanding how we can come into play with the liquid air interfaces or the material interactions like the silicon oils that are in a lot of dosing syringes. From here, I'm going to go ahead and hand it over to Dr. Chow to go ahead and describe some of the other issues with aggregation phenomena.
First, I want to say that my purpose here is to speak from the perspective of a pharmaceutical scientist, specifically that of a biopharmaceutical scientist. And now, as some of you may know, the major distinction between small molecule formulation development and biopharmaceutical formulation development, or more specifically, proteins, is that proteins have, in addition to chemical stability, also have physical stability. And obviously, when we're talking about aggregation, we are referring more to the physical stability aspect of protein pharmaceuticals. And why is it important? It's very important because aggregation is one of the key limiting factors that could prevent a protein molecule being successfully developed into a medicine. And it is, in fact, a very hot topic from the regulatory point of view and the whole industry because it impacts the safety and efficacy of all biopharmaceuticals, which is why we're focusing on this today. And the reason why I became interested in this technology that's called ARGEN. So let me talk a little bit about some of the key things beyond what Mike mentioned about what factors that influence protein physical stability. As Mike stated in his simple two-step model about how protein may denature and the denatured protein may go subsequently form clusters and form aggregates of different sizes. In reality, obviously, it's not much more complex than that, as you can see on this slide, because proteins can aggregate as native proteins as well as partially unfolded or fully unfolded protein. And for this reason, as a pharmaceutical scientist, it has always been my desire to focus on finding analytical methods or ways in which we can analyze the aggregation status of protein pharmaceutical in its form without any further manipulation. One of the most classic form of manipulation is dilution of the sample. And we know that the concentration of the protein frequently can alter the level of aggregates that are formed that actually exist in that solution. And which is one of the reasons of why I became interested in learning more about the technology behind ARGEN. Okay, and now if we can go on to the next slide, please. Mm-hmm. So aside from the conformation stability that might influence whether the protein will denature more readily, as well as the colloidal stability that will influence the nature of protein-protein interaction, whether it be attractive or negative, is this very important stability we call interfacial stability. And the reason behind that is the mechanism behind how protein aggregate under interfacial stress is fundamentally very different than that you encounters during thermal stress, or what happens during when you turn a low concentration protein into a high concentration protein solution, in terms of how colloidal stability influence the viscosity or basically the aggregation status. Interfacial stability impacts the protein stability because there's interfacial tension in the air-liquid interface, as well as other interfaces like solid-liquid, even liquid-liquid interfaces, like silicon oil and water interface would be one prime example that has a very important influence on the development of biopharmaceutical today, especially when you are formulating them in prefilled syringes that have silicon oil. And therefore, it is very important when we evaluate formulations, we not only look at the temperature stability, we also look at how the protein responds to interfacial stress, and importantly, be able to monitor the response of the molecule to different levels of interfacial stress. Okay, now with that, I can go to the next slide, please. So as I mentioned, for over 15 years, I have personally, and through my experience of various organizations, looked at many analytical methods that are commonly used to monitor aggregation. The list is getting longer and longer every year for the reason I mentioned that there's a great need for analytical methods that can basically have less deficiencies than we have currently available. And as you can see on this table, which actually dates back about 8 years, today the list has grown. However, there is still a great need for analytical methods that fulfill a number of criteria. And I mentioned just a few of those, in my opinion, as pharmaceutical scientists. I mentioned earlier about the one where we would not have to alter the concentration of the sample. And the most commonly applied method of size exclusion chromatography is a very classic case of how the analytical method itself can alter the nature of the aggregate in the sample because of dilution, and also because of the interaction between the aggregate with the HPLC column itself, as well as a number of other factors, which is exactly why sometimes when we do not see any aggregates on the SCC, yet we can actually see them with our naked eye. So there's a lot of inconsistency, even between method to method. And importantly, a lot of the methods we have that we traditionally use to develop formulation actually can only take a snapshot of the status of that sample over a period of months, weeks and months. And that just simply takes a lot of time for one to be able to decide on what is the optimal formulation. So you can see here among this list, yes, you can see there the standard light scattering method, which is the basis, the theory behind the ARGEN technology, which Mike will talk in more detail about, is listed on there. However, the conventional standard light scattering instrument often is used in line with the HPLC, or is basically used to measure the absolute molecular weight of aggregates in solution. However, there's not really anything available that I'm aware of that can perform real-time monitoring of a protein's aggregation status under both thermal and agitation stress or stirring stress. And so that's what made me a little more intrigued about it, and which is why we evaluated the technology. I, in cooperation with Fluence Analytics, have been looking at how to turn a tool like this in combination with our understanding of protein stability to develop better formulations. Okay, next slide, please. And so I mentioned the need to be able to make decisions in less time. That's because today in the biopharma industry, we have a very large development pipeline. And the scientists are always faced with an increasing demand to develop more formulations in a shorter amount of time. And I mentioned about the fact that to get to the root cause or the mechanism of aggregation, it means that the closer we get to when the aggregation actually occurs, the better chance we have to actually make sure that we are trying to control or minimize that degradation based on our understanding that mechanism rather than half guessing. And which is why it's my belief that real-time monitoring of the changes in the protein's aggregation status presents a very unique advantage. So today, we need to have analytical tools that can simultaneously stress protein while monitor aggregation kinetics in real time. And I said, being able to stress as well as monitoring, because what we do today is that we put samples under stress, and then we take the samples out and put them on the various analytical methods. So there's a major gap in terms of time between when we actually stress the samples and when we actually see the data. And lastly, I mentioned that it's very important that we try to use complementary methods, between different methods to verify the findings from traditional methods that we're using for quality control, like SCC, HPLC, to ensure that the decisions we make during formulation development will not later on be found out to be incorrect, which would really risk a tremendous amount of development time and ultimately whether a molecule can ever make it to the market and to serve patients. So the rational approach for developing protein formulation is to really make sure that you understand whether the conformational stability or colloidal stability, there's a relative degree of influence on the protein's aggregation rate in solution. And then thirdly, you want to make sure that you are measuring the protein's response to interfacial stress in order for you to rationally select the type of surfactant as well as the level of the surfactants to protect the protein against the interfacial stress. And then number four, and then finally, is that you want to make sure that you are going to use the combination of different stress along with the response of the different formulation parameters and how they impact the protein stability under those different forms of stress. So you can come up with ultimately the optimal combination, not only the type, but also the relative amount of those excipients to be able to protect the protein. And with that, I will really turn over the presentation to Mike.
All right. Thank you, Danny, for that introduction. It was actually quite a bit of grateful information to introduce the issues with the current technology and why we need a new tool like this. We at Fluence Analytics have developed what we call the ARGEN, Aggregation Rate Generator. The key benefits from this is that it uses a light scattering technology to monitor the molecular weight of the molecules as they evolve in time. So as the signal increases, we see an increase in molecular weight. We do this on 16 independently temperature and stirring controlled cells. This gives us the benefit of doing large differences in formulation screening. This information gives us early detection of aggregation and degradation, or in some cases fractioning, as we'll look at some cases later. Since we're monitoring this in a real time and in a kinetic manner, we don't have to wait for months for an aggregate to form. We can actually see it as it's forming. The key outputs from this information, we get the aggregation rate, which we'll discuss shortly. the normalized molecular weight, which I'll also point out, and then also the mass aggregation rate, so you can actually get a little bit of information about how big these molecules or these aggregates are forming. And this information goes into applications for formulation stability, interfacial studies with different materials, glass, metals, oils, and things like that. Also, GPC scheduling, as Danny was discussing, is knowing when to take a sample and then inject it into your GPC or HPLC system. And as well as dissolution kinetics, knowing when your samples have actually dissolved into the buffer solutions or the formulations that you developed. So let's take a look at what the aggregation rate is. The aggregation rate from this plot on the graph on the left side of the screen here is actually from an experiment where we monitored the sample under a thermal stress. If we look at this early phase data right here, we see that there's not really anything taking place. The signal's pretty stable. We call that the M0. The M0 marks the unaggregated mass of the molecule, or the monomeric form, as a lot of times it's called. This increasing signal from here is actually, as I mentioned, an indication that aggregation is taking place because the molecule mass is getting larger due to the aggregation itself. So if we look at this early linear phase regime of the aggregation, we can get a rate information from this. We have to look at the very early phases of this because we want to get it before we start to see secondary and third levels of aggregation come into place, where you have dimers and trimers starting to aggregate together as opposed to the individual molecules themselves. This information, once you have the weight average molecular weight increasing in kinetic time divided by this early M0 mark, is what we call the normalized ratio of the aggregated mass with respect to the unaggregated mass. The time derivative of this value is actually the rate of aggregation, which we're going to be using to describe and define a lot of the information that we're exploring with the ARGEN technology from here out. So now we understand a little bit about what we're actually generating with the ARGEN system. We're going to use this information to go ahead and show us how we can use the technology for understanding kinetics of thermally stressed monoclonal antibody for case 1, discovering stability patterns in BSA from 3 different types of formulations. And then we're also going to look at how we can use the both thermal and stirring stresses to look at quantifying which sample is the most stable between a set of peptides and different formulations. And then taking all that information, we'll look at how we can use the technology to screen formulation conditions to develop an actual formulation for a particular case, in this IgG, immunoglobulin G. So first case we're going to look at, as I mentioned, understanding the kinetics of a thermally stressed monoclonal antibody. So looking at this graph on the bottom left corner here, we see that there's an aggregation profile for a lot of different samples. The key thing that we want to point out here is that we see the aggregation profile for all these samples at different temperatures. So there's no quantifiable temperature of aggregation where the sample just starts to aggregate. We see that this happens at all these different temperatures, but well, as we understand, it happens at different rates. What I want to point out here is the bottom time scale here. This is a log scale. And the reason for that being is because at the higher temperatures, we can see that in about 45 seconds, we see a significant amount of aggregation for this particular sample here. If we look at 14 hours later, we can see that the signal from that particular sample at 50 degrees Celsius, which is still pretty high temperature, there's a very low amount of aggregation behavior that we've been observing from this sample. Now, understanding what we previously produced on the previous slide, where the aggregation rate, we could take that aggregation rate and then build what we call an Arrhenius plot. This is it's a pretty typical plot for a lot of kinetics and understanding of rate limiting issues. If we take the aggregation rate and put that on the y-axis and then plot it versus 1 over the temperature in Kelvin, we get some information about the activation energy, but also we identify these 3 real distinct regimes of aggregation, which we're going to use throughout the rest of this presentation. First, I want to point out this high temperature aggregation profile in red. We call this a denatured profile because at this temperature, we've actually fully denatured the molecule. We've succumbed over the melting temperature, the TM, for that molecule, so that there's no actual unfolding taking place here. It's all fully unfolded, and the molecules are coming together by the rate of diffusion throughout the solution itself. Taking into account the secondary one here, between the temperatures of about 65 to about 55, we see that there's a linear regime where we actually, the rate limiting factor here is the temperature and how that temperature causes the unfolding of the molecule to take place. In this case, we can actually also identify the activation energy of how much energy it takes to start unfolding those molecules. Now, thirdly, and most importantly in our opinions, is looking at the stochastic regime down here. The stochastic regime to be identified is a lot of different factors come into play, as Danny was mentioning, you know, the interfaces with the liquid air materials, glasses, silicon oils, and things like that. A lot of things that are not thermally rate controlled cause aggregation as well. And this is really what causes a lot of headaches at the storage conditions and longer term studies, is you don't really see this, you know, quick quantifiable snapshot until you understand really what's going on with these stochastic regimes. So we understand that this happens at lower temperatures, but we want to get a hold of what's actually taking place down there. So now, understanding this, what this Arrhenius plot is and how we can get information from it, we're going to go use this for discovering the stability patterns of, as I mentioned, bovine serum albumin. In this formulation, we developed 3 different pHs. This experiment was produced in about 3 days, 36 different types of experiments, and all isothermal conditions. We measured the aggregation for these different formulations across different temperatures to build up this Arrhenius plots. Now, if we take all 3 of these data sets and plot them together, we see, you know, quite a drastic difference between what we say is the Arrhenius kinetics and behavior of those samples. If we look at the top part of this graph where we see the data represented by 4.75 pH, we see that there's a, you know, an aggregation profile here. We have a high temperature zone and then a medium temperature zone. And we didn't really push it to much lower temperatures because we, you know, wanted to expedite this experiment. But now, if we take this information and look at the pH of the 6.75, we can see that the overall aggregation rate of these 2 different samples has been significantly reduced just by increasing the pH. This is a indication that we've matched some colloidal stability of the solution here because we've overall dropped the aggregation rate, but without changing the difference between the high and low temperature regimes. And this is also indicated by the fact that we see the activation energy. There's not much difference in there. So it doesn't, we haven't changed the conformational stability of the molecule, so it still takes about the same amount of energy to unfold the molecule to produce aggregates. Now, thirdly, if we look at this lower part of the graph where we see the pH of 2.75, and we say, let's step back from this and say, okay, the lowest aggregation means it's the most stable, which is, you know, something we're going to talk about on the next slide. Overall, we see that there's no real different regimes between the high and low temperature, and it has the overall lowest aggregation rate between the 3 different pHs. What we're going to point out next, if we take one snapshot temperature from all 3 of these different experiments, in this case 55 degrees Celsius, and we plot all 3 of these with respect to the aggregation kinetics on the time scale, and we see this is about a 100-hour experiment, so these samples were sitting there aggregating for quite a bit of time. If we look at this on the left side of the graph, we see the pH 4.75, which the previous graph with the Arrhenius kinetics pointed out that this is the most unstable sample. We see that the aggregates within, you know, 1/10 of an hour, we see a significant amount of aggregation taking place here. If we look at the sample in blue, the pH 6.75, the same amount of aggregation took place in about, you know, somewhere up to 90 hours. So it took quite a bit longer to aggregate. And we can point this out that it's about 600 times more stable than the sample at pH 4.75. Now, overall, we, you know, in the previous graph, we quantified that the 2.75 is probably the most stable. But if we look at this information and actually take an understanding of what the kinetics of aggregation are actually giving us, we can see that this light scattering signature, as it's degrading over time, is the indication that the molecular size is actually getting smaller and smaller. And this is likely due to fragmentation by hydrolysis. We can actually identify that here that we've seen a negative aggregation rate. So overall, we can quantify that the 6.75 is the most stable of these different formulations and the most viable sample for formulation development. All right, so now we understood a couple different cases. We're going to look at how the ARGEN can characterize the differences between thermal stability and stirring stability. Now, I'll point out that ARGEN as a technology can actually stress the sample, both stirring and temperature stress at the same time, while, as Danny said, by not changing the conditions of the solution. So we're not affecting any other conditions like the concentration or dilution, or we're not sending these samples through columns which could then break down aggregates as they flow through there, or interactions with the columns themselves. So we're going to point out here, if we look at the top left graph, we see something similar to the previous couple of graphs where we see the aggregation profile over time. In this case, it's about 48 hours. The differences here is that we had two different samples of peptide in two different formulation conditions, one at pH 3 and one at pH 2.5. The temperature was held constant at 18 degrees Celsius, but there was no stirring on these two samples. And what we understood from these is that there's really no significant aggregation taking place under these conditions under thermal stress. But we take another look at this. We take two new samples with the same pH conditions and the same temperature, but we stir those samples while monitoring them in continuous fashion so we get the aggregation kinetics. We can see that there's a big difference in the overall stability of these two different samples. We see here that the pH 2.5 is much more stable than the pH 3.0. By looking one at the graph on the bottom left here, to see the sample in blue aggregated much faster than the one in the red. But if we look at the aggregation rate from those two samples and look at that on the graph on the right, we can see that there's an order of magnitude between the aggregation rate between these two samples under these conditions. So what we've done, we've shown that under thermal stress, we have a pretty stable molecule in this particular formulation, but under stirring stress, where we want to understand these stochastic effects and interfacial effects, you have a more likelihood of interactions with these molecules. You can see that the aggregation behavior from these two different samples is quite different. And overall, we quantify that the sample at 2.5 pH, as well as the temperature of 18 degrees Celsius and stirring, is the most stable of those different conditions. Danny, did you have anything to say about that?
Okay, Mike, I think it's worth pointing out in relation to my introduction of this talk is that we see here that even at the same temperature, under this, what is considered low sub-ambient temperature, that the interfacial stress induced by stirring the sample could really destabilize the proteins in solution. And these are the cases in which if you add so-called conformational stabilizers, you won't really impact the stability during stirring. Now, interestingly, you see here that even though there's no surfactant added, no excipient added, just by having a different pH, you see a difference in aggregation rate. And I want to point out this is most likely to the difference in this colloidal stability between the two different pHs, where one, the protein interactions is relatively less attractive than the other one. And obviously pointing out to the lower pH sample, probably having better colloidal stability. And also want to quickly point out that your data with BSA very nicely illustrates that when the two solutions have a similar temperature in which the transition going from the low temperature scheme to the high temperature scheme, we can see here that the break point or the inflection point there is around 65 degrees for both the 4.75 pH and 6.75 pH samples. Despite that, there's a big difference in aggregation rate. And when you showed in the data on the following slide, illustrates again how it is this kind of phenomenon is contributed by colloidal stability of that formulation rather than by the thermal stability, which is why it's very important to see this to better understand the key mechanisms that are driving aggregation so you can select the right parameters to change.
Great. Thank you for the input. Good. I'll move back up here to where we're moving ahead. Okay, so now we've seen a few different cases where we use ARGEN technology to differentiate between different samples and their stability. Now we're going to use ARGEN technology to develop a formulation for a particular sample, in this case an IgG. So we'll first look at the kinetics of aggregation for the sample as dissolved in plain old DI water. We see here that there's a similar type of aggregation behavior, a high temperature, a low temperature, and then what we call the stochastic regime, where at the low temperature, different interactions cause more propensity to aggregate than the thermal dependent aggregation. So what we want to do is develop a formulation for this molecule in this different type of formulation conditions so that we reduce this effect at lower temperatures. So our first attempt at this was screening a buffer. So in this case, we chose one temperature, 55 degrees Celsius. We set up 8 different samples and serially increased the concentration of the sodium acetate in this case, so we can then identify what is the optimum concentration of the buffer to mostly stabilize the sample without going over. In this case, we identified at about 25 millimolar of sodium acetate, we've reached a lowest aggregation rate for these different conditions. These are all held under the same temperature, all the same different same molecules, but the only thing that was changed was the concentration of the buffer here. What's interesting to point out is if we go beyond 25 millimolar of the buffer, we can actually drive the aggregation rate back up, all the way up to about 200 millimolar where we stopped the condition testing. We can see that the aggregation is almost equivalent to having no buffer at all. Now, understanding of this information, we moved to the next step where we tested different concentrations of an excipient. In this case, we screened the concentration of sucrose with this molecule. The same conditions were held here, 55 degrees Celsius of temperature with no stirring taking place. But what was interesting is we ramped the concentration of sucrose up from 0 millimolar up to 600 millimolar, and we see a minimal aggregation rate again reached at about 200 millimolar of excipient concentration. What's also interesting is we see that if we continually increase the concentration upward of 400 or 600 millimolar of sucrose, we don't get any additional benefit from the extra concentration. And in most cases, this can actually usually turn into some inhibitor or some other issue with the formulation development. So we like to say, you know, just enough is good enough to develop the formulation. Now, taking these two things into account, we developed the formulation, we mixed the solution together, and we did, again, the Arrhenius kinetics on this sample to compare with the non-formulated value. Overall, if we look at the blue data here, we see that the overall aggregation rate is roughly about 10 times lower for each temperature going across the different temperature regimes from high to low. We see that overall it's much more stable. But what's most important, if we look at the bottom right of this graph here, at the lower temperatures where we reach 40 degrees down to 30 degrees, we can see that we've developed a formulation that's actually increased the stochastic stability of the sample. And this gives the user or the formulation developer much better capability of predicting the shelf life and the incubation stability of these molecules under this formulation over time. So this is one example of how we use the tools to actually screen the lowest propensity to aggregate from different conditions and develop the formulation, which really only took about a week for this conditioning to develop. Danny, do you have anything to add for these?
Hey, thanks, Mike. I think the key idea here, perhaps I could add, is that we could see from this graph here that having the right formula, having a stable formulation, reduce aggregation rate across the entire temperature range from 30 degrees Celsius to over 70 degrees Celsius. And of course, we know we will never utilize 60 or 70 degrees Celsius as a condition to evaluate stability with protein formulation. But we can still see how the stability of the formulation allow the aggregation rate to be lower under the conditions where protein typically are denatured. However, the impact of the formulation has on what the temperature that's closer to what we typically use for stability study, i.e. 40 degrees and below, that is most striking. As we can see that using this approach, we could see how aggregation rate really is minimized under the temperature that are typically used to run a formulation study. And as you mentioned, this only takes 1 week to discover this. And in contrast, what we typically see, it will take at least 4 to 8 weeks when we do it the traditional way.
Thank you. All right, that's great. So let's move to the next slide, which is we're going to start summarizing things here. Argen's key benefits. Efficiency. As we saw, the abilities of Argen to quickly develop formulations using these 16 independent sample cells and the ability to stir and temperature control each of these samples gives us a good ability to screen excipients and conditions for formulation development very quickly. Versatility, some of the things we didn't look at today was the ability to understand how the absolute molecular weight and viral coefficients can also be understood to develop conformational stability or colloidal stability of the molecule in those different solution conditions. Kinetic information, as we saw in one of the slides, is a very strong tool for pointing out the differences in overall stability. We develop understanding about how these molecules evolve over time. Even if it seems they're stable, we understand that maybe there's something else going on here to understand like the hydrolysis or degradation or fractionation of the samples. And then stability. As we understand now, the analysis of this aggregation and degradation of the sample in the formulation, as well as a parallel kinetic screening of the samples, gives us a powerful tool for understanding how aggregation develops in time, as opposed to just taking a particular snapshot 1 month, 2 months, or 6 months down the road when aggregation may have taken place, but you don't know how it happened. Did it happen very quickly, or did it happen very slowly over time? And how can the screening and the formulation development reduce that propensity to aggregate and reduce the aggregation rate overall? And with this, I'll give it back to Danny, and he can present the information about our paper together.
Okay, thank you, Mike. So as I mentioned in the beginning of this webinar, I think the best way to discover or to learn about any tool that has a utility, in any development effort, is to actually use scientific approach to evaluate it. And that's exactly what we did, after I was introduced to ARGEN. And in fact, we did a study to look at how to combine analytical methods like ARGEN, high throughput methods, in conjunction with what we call rational scientific approach to formulation development, to be able to develop the formulation in a more rapid time than ever before. And I invite you all to read this article, the reference here, for more information on how we do that. And have any questions, and we'll be happy to answer them. Thank you.
Thank you all.
Thanks, Mike and Danny. We'll move into the question session right now. So if any of you have questions, please send them through the chat feature located at the bottom of the screen. Just scroll down. Our first question is, are models used to relate to light scattering with ARGEN?
I can go ahead and answer this one. No, actually, since we're using light scattering, we don't need to develop a model for it. One thing we do have to take into account is that with this particular model of the ARGEN technology, we're only looking at 90-degree scattering. So there is an understanding that you're not getting this extrapolated value, which would be understood by the Zim plots with multiple angle scattering. But with that taken in mind, we do have an understanding of the aggregation molecule size at t equals 0 before any aggregation takes place, and then how that evolves over time. So.
Okay. The next question is, can ARGEN replace any of the current analytical methods that were referred to on slide 6?
Danny, you want to?
Okay, sure. Thank you, Matt. So I think the best way and the most, and the objective way we can answer this question is that ARGEN is not, a technology like ARGEN is not necessarily meant to replace another analytical method. However, that I could say that there is an other analytical method that by itself can do everything that this particular ARGEN technology can do. And I think the closest analytical technology, as anybody familiar with this field would know, is that there are static light scattering based instruments on the market, and they're very good. They're very good technologies that are well established. But if we look at what's currently available, static light scattering is interestingly most frequently used nowadays to actually verify that the data from SEC is true. In terms of the actual, whether a so-called dimer peak is truly a dimer versus that of a trimer or tetramer. So that shows you that the standardized scattering, the theory is robust because it's basically a century-old theory and well-established models. So there's no, like Mike said, there's no need to develop any new models. But I think I can safely say that there's no standardized scattering instrument that actually is intended to monitor the kinetics of aggregation. And I'm not aware of any standardized scattering instrument that can perform both temperature stress as well as interfacial stress by stirring at this moment. Again, this is what we have today. And as a scientist, we are looking for solutions. And so that's why, to me, something that can provide the kinetic information under different forms of stress is meaningful. So it's not meant to be necessary to replace anything, but it does have this distinguished feature that's worth evaluating.
No, thank you, Danny. That was a very good summary.
Thanks, Danny. The next question, when you screened the IgG, did you look at aggregation rate at 25 degrees Celsius? What did that look like?
Okay. With this particular example, we did not go down to 25 degrees Celsius. We have the ability to do so. These experiments that we monitored this, for this formulation development, we stuck between about 30 degrees Celsius up to 80 degrees Celsius. And that was mostly because we want to look at the aggregation kinetics in a short period of time. As we saw, the lower the temperature as we develop the formulation, the longer and longer it takes for the sample to aggregate. So if we wanted to do those studies, which we openly invite people to ask us to do so, if we want to do some kind of collaborations together, we can monitor those samples at 25 degrees, which with non-formulated samples, we see there's probably going to be some significant amount of aggregation taking place. But after we develop a formulation, we might be waiting a good week, 2 weeks, or 3 weeks to actually see some aggregation taking place. But why wait all that time when you can screen this information out in about a week?
Thank you, Mike.
So Mike, if I may add, I add a little bit to this answer, which is, very, your answer is perfect. But if I could add something, that would be, it's very important that when we screen for, formulations, the stability of any protein, that we look at the effect of thermal stress and in interfacial stress separately. Okay. Because there are different mechanisms in effect, so that if we simultaneously try to use heat as a stress to stress the molecule while applying stirring stress, especially if we get into temperature scheme that's getting closer to protein unfolding temperature, then the results will often be very confusing and not meaningful. And that's why even though ARGEN can do both at the same time, it is not something I would recommend if you really want to, use it in a way to help you to better understand the mechanism that's truly at work.
Thanks, Danny. The next question, have you found the aggregation rate predicted by ARGEN corresponds with that by real-time stability?
All right, thank you. It sounds like this question is actually directed at those lower temperatures again. What we're working on now is actually a study where we take and quantify and rank the stability of the different formulations to predict which ones are going to be the most stable over long periods of time. That study's underway, and hopefully we'll be able to give a presentation on that information probably within the next few months or 6 months or so. Because as I mentioned in the previous question, understanding those kinetics takes a bit longer because you have to wait for the aggregation to take place. And then also ranking the stability, quantifying which sample and which formulation is going to be the most stable. As Danny pointed out in one of the previous slides, there's a lot of tools to kind of characterize the aggregates after they've formed, but not the rate of aggregation as they've formed. So understanding, has a sample aggregated over time in about 6 months, what is the aggregation development? Is it a dimer, trimer, or something further along? That's where we were looking at characterizing and quantifying the information there.
Thanks, Mike. The next question, has ARGEN been used to monitor peptide and protein chemical synthesis reactions?
Yeah, we've actually looked at some of these interactions with peptides and stuff like that. The tool actually, since it is a light scattering, monitoring molecular weight evolution as is, say, we can actually see this polymerization or peptization of different peptides as they interact with different pegs and stuff like that. So yes, we have looked at that. That was done more on a research topic with a particular customer and under different NDA kind of conditions. So we can't present that data today until we get some information, permissions to do so. But we're open to doing some of these studies with a collaborator that's interested in looking at this type of stuff.
Thanks, Mike. The next question, have you used ARGEN to monitor folding?
Unfortunately, no, we do not have fluorescence detection, so we don't get the opportunity to monitor the folding or unfolding. We can see the results of unfolding as aggregation takes place, but without the fluorescence, we don't get that tryptophan signal to give us an indication. This is something we're working on and developing, and hopefully in the next year or so, we'll have a development where we can actually monitor the fluorescence as well as the aggregation rate over time. Danny, would you actually have any other input on that?
Yes, this is an excellent question. So as Mike mentioned, monitoring the aggregation rate will not itself tells you the folding status of the protein, under any temperature. However, in our study, and again, referring to the paper we published, and as we use another orthogonal technique that actually looks at protein folding, in that case, it was actually differential skinning fluorometry. And what we incidentally found was that the unfolding, the protein denaturation onset temperature detected by nano differential skinning fluorometry happens to match that, basically that temperature in which we begin to see the differentiation from the lower temperature aggregation, the activation energy versus the high temperature scheme. And so I have seen this with multiple molecules. So I don't believe it's a coincidence, and but it will take more study, more research to verify this finding. But I think when we looked at basically 25 different same molecule in 20 plus formulations with different levels, with different unfolding and onset temperatures, and they coincide with what we see in terms of that inflection point, I think that's a very interesting data, the insight that we got from the studies.
Thanks, Danny. So we don't have any more questions. Danny, do you want to leave the attendees with some final food for thought?
Well, I think, no, thank you, Matt. So I think my final message to everyone is to, in order to, just like someone asked, I think the conventional way our industry develop formulation, any product today, is to use the analytical techniques that we are used to, because oftentimes these analytical techniques are easily more validated for use for quality control. But it's not increasingly, apparent now to everyone, including the regulators, that these techniques have very glaring deficiencies. And that's the reason behind all this effort to look at alternative technologies, to look at protein aggregation as well as the formation of particles that are larger aggregates of protein. And so when we want to answer the question of can we correlate ARGEN data with what we know today, the question is a big maybe. And Mike answered it correctly by saying that we're doing, there's more research going on. But we want to be very mindful that when you compare, trying to compare the data for a technique that basically tells you exactly what's going on versus techniques that have issues in terms of altering sample, altering the nature of aggregates, and also is notorious for a lack of reliability, because many proteins have been developed into commercial products that were found to be stable when they were released by these same quality control methods, yet later to actually form particles. And this is one of the major challenges we face today, which is the reason why behind my passion to search for a different solution to this problem. And so thank you for the opportunity to share my insight, and look forward to meeting all of you sometime in the future.
Great. Thank you, Danny. Again, I'd like to recount Danny's thanks there, and I'm also very thankful for having all the attendees here and the questions, and I'd like to follow up with anybody else separately and help us also understanding more useful cases for the ARGEN technology, different applications for the technology itself, as well as understanding how we can help you all. All right, with that, I'll have it back to Matt to go ahead and close out.
Again, thank you everyone for joining us today. Our website is fluenceanalytics.com, and if you have any emails that you want to send to us, you can email arjun@fluenceanalytics.com. As a follow-up, I'll send out the PowerPoint presentation that we presented today, as well as a link to the recording of today's webinar. So again, thank you for joining us, and we hope to hear from all of you soon.
Thanks. All right. Take care, all.